There are two ways to make your code faster. You can either delete it, just eliminate it, or reduce the amount of stuff your code is doing. But we got problems with this. So if we just say, let's delete the code, well, then what are we going to get paid to do? I kind of like eating. I like being paid for the work that I do. I like having work to do. So we can't just delete everything that we're writing. Sometimes you can delete some stuff and swap it out for something else, but that's more like reducing the stuff. And at some level, there's only so much you can reduce as far as the stuff is concerned. Like maybe that stuff is actually the stuff that you're trying to sell. So you can do these optimizations, but at some point you get to this level where it's like, well, I can't get rid of any more code. I can't reduce the stuff it's doing. But before we get into caching, I thought it was really important for me to talk about these two things first, because caching is a pretty significant challenge, and it brings it along a lot of complexity. And so I wanted to call this out because I have this idea that I like to talk about called don't solve problems, eliminate them. And by that, I mean, we've got this really, really big problem of caching. And if we just go for that solution right out of the gate, we might actually miss the opportunities to actually just change our approach where we actually don't need caching at all. And I have something also relatively similar in this vein called Fix the Slow Render Before You Fix the Re-Render. This is a React-specific post, but the idea is if your re-render of your component is really slow, then reducing the amount of times that it re-renders is fine, but if you speed up how fast it re-renders, then you won't care about how many times it re-renders. And so looking at ways to make it so you don't have to cache is much better than figuring out how to cache. That's the point. But for a lot of situations, you can't delete it, you can't reduce it, and you can't just make it fast. And so for that, we're going to cache it. Unfortunately, we're not going to cash it. We're going to cache it, which is not nearly as fun, I promise. But it can be kind of interesting and fun, so let's talk about this. What is caching? So Wikipedia says, in computing, a cache is a hardware or software... No, that's ridiculous. I'm not going to read that. Let's look at examples instead. I think that will be a lot more efficient for us. So here's a function called compute_pi that computes a certain decimal place of pi. And if we wanted to cache this, it would actually be pretty straightforward. So we add a variable outside of the function. We have this special function that's our cached version of compute_pi. We check whether pi is undefined, and if it is undefined, then we'll compute pi, and then we'll return it. And then the next time this is called, pi will be assigned. So we'll actually skip on computing pi, and we'll just be able to return pi right away. This has really two nice benefits. One is we don't have to pay the cost of calling compute_pi multiple times, which means it will speed things up because we don't have to go through the process of this entire function. But then the other one is if for some reason we have to pay money to call this function, we don't have to pay that money either. And that may sound ridiculous, but think about this as like a third-party API you need to call. If you're able to cache the result of that third-party API, then you don't need to call it. And so now you don't have to pay the money that it costs to call that API, just as an example. So this is a pretty simple example. It's actually, in some ways, it reminds me of the singleton pattern that you might be familiar with. Yeah, it's a pretty simple example, but let's pull out the things that we can learn from this and what the fundamental idea of what caching is. So you store the result of a computation somewhere and return that stored value instead of recomputing it again. That's it. That's what caching is. That's all it is. Storing the results somewhere and then returning that stored result instead of recomputing that result every time. I wish it were that easy all the time though. So let's look at a little bit more complex example. Let's add a precision argument where people can specify how many decimal places out on pi we want to compute. So this adds quite a bit of complexity because before we had a hard-coded amount, but now people can change the precision as much as they like. And so we have to change our caching strategy a little bit. And it's not all that bad. So now we have this pi cache, and it's an object this time. And then we say type of PyCache at this part of the object. So we can kind of have a mapping of the precision to its result. And so then we set that to compute pi. And so if we're calling compute pi cached with the same precision multiple times, then we won't have to call compute pi for that specific value. And this brings us to another concept called cache keys. And the key in our case is this precision value. But the key is actually a pretty tricky beast. And I think we're going to need a different example to get an idea of why the key is a little bit tricky. So here we have a sum function. It's still like super simple. We have our sum cache that's just an object. And then we take 2 arguments. And now we have to compute the key in some way. So in our case, we're just going to say the first argument with a comma and then the second argument. So that way we can always make sure that given the same 2 inputs, we give the same results. And so then everything else is the same. I think this would actually be useful to kind of watch what the code execution looks like. So let's watch this. First, we're going to call the function. We generate the key. It's 1, 2. That's not in the cache. And so we call sum. And then we get the return value, which will be 3. So we're going to just return what we just barely set into the cache. And now with that, our cache has that 1, 2 in the cache key. So now when we compute the key, it's going to be the same as before. And so when we check in the sum cache, we're going to have a value for 1, 2. And so we can skip over that if statement and just return the value in the cache. So that's how we're able to skip over recomputing the sum, is because we calculate the same cache key that we had before for that same value. So that is cache keys, but there's a pretty significant challenge with cache keys. And that challenge is visible right here. So I want you to play a little game with me. Actually, I want you to pause the video, find the bug. There's a bug in here that is really bad. And yeah, go ahead and take a second, find the bug. Did you find it? Okay, so the bug is right here in our key. Our key is incomplete. So let's look at the specific example. So we call add days cached 3. So we want to add 3 days from today. And then we call it again. We get 3 days from today again. That's our cache hit. And then if we wait 24 hours and our program is still running, so that cache is still there, then we call it again with 3. Now we want 3 days from that 24 hours later, right? And unfortunately, that would be 3 days from yesterday, which is 2 days from today. So we got the wrong answer here. And that's because our cache key was incomplete. We got a cache hit, and we definitely shouldn't have gotten a cache hit. So yes, we have ourselves our first wonderful caching bug. First of many, I'm afraid. Poor Homer, I'm so sorry. So cache keys are tricky. The cache key must account for all inputs required to determine the result. Unfortunately, in our case, one of the inputs is date.now. And so, yeah, that's not going to work. So there's a caveat to cache keys, or like we kind of end up cheating a little bit. So first, it's easy to miss an input. We'll look at examples of each one of these. You also could possibly have too many inputs, and computing the correct cache key can be costly. That alliteration is intentional. So let's talk about missing the input. So it can definitely be easy to miss an input. If you've ever used React and use memo or use effect or use callback, this dependency array, those are inputs into a cache. And yeah, it's very unfortunate, actually. It's so tricky that we need an ESLint plugin that doesn't always work exactly the way we would expect. So yeah, really easy to miss inputs, and really like devastating to miss those inputs, as we saw with poor Homer. So especially like in when you're writing it from the very first, it can be relatively easy to miss an input, but also as you're making changes to existing code, you can add inputs without actually really knowing. And so yeah, easy to miss an input. Also, could have too many inputs. So a good example of this would be Google Flights. There are just an outrageous number of possible inputs for the results that you get here. So it's like the origin destination, and the ultimate destination, the dates, and then all of these filters like which airlines you want, the stops that you want, the bags, the price, the times, emissions, connecting airports, duration, all of this stuff results in just so many inputs that you probably would never even get a cache hit because it's going to be different. And in fact, it's very possible that Google uses my own user history as an input into this that I don't even see in the UI here. So yeah, there are too many inputs. Now, there are probably lower level caches because they're probably talking to third-party APIs for getting the flight information. Maybe they're caching some of that stuff. But yeah, for caching the entire page, that's not going to happen. No way. And so I don't have any insider input into or view into how Google Flights works, but I'm pretty confident they do not cache this entire page. That just would not work. Too many inputs. And then another one is computing the correct cache key is costly. So for my personal blog, all of my blog posts are actually MDX files on GitHub. And the compilation process can take a couple hundred milliseconds to compile a blog post. And the input for compiling that blog post is going to be this MDX file. Well, getting that MDX file string contents, that actually comes from GitHub. And so for me to use like the proper key for the compiled blog post is the MDX input string. That like, the entire thing would be the key. But that doesn't really work because getting that entire string requires going to GitHub, which is going to take a couple hundred milliseconds itself. And so computing that cache key just is not reasonable. Like the only thing that I really have is the slug in the URL. And so I don't really have a great way to have a cache key that is a reliable cache key for compiling this blog post. So that's not going to work. So we're going to cheat. We're going to start doing some cache revalidation. We're going to acknowledge and embrace the fact that we don't have the ability to provide all cache keys, and we're going to revalidate. And there are a couple different approaches for this. So let's talk about cache revalidation. So there are a couple options. You can proactively update the cache. So for example, on a post update, you just update the cache. I have a GitHub action where every time I make a change to content, it tells my server that's actively running, and my server will say, oh, great, let me, I'll keep on serving cached versions, but while that's happening, I'm going to go to GitHub, go grab that MDX that was changed, and update the cache so that the version that I'm sending is a cached version. So that's the approach that I take. It works really well. It can definitely fall out of date, like if the GitHub action fails for some weird reason or something. And so having a couple of these other strategies is still useful, even if you're doing that. Another approach is timed invalidation. A good example of this is cache control headers. So when a browser makes an HTTP call to a server, that server can send a header back on the response that has a couple directives for the cache control. And one of those is max age. So you can say how long you want this HTTP response to be cached in the browser cache. The browser has a cache built in. It's awesome. And so you can say, I want this to be assumed valid for 60 seconds. And so if the browser makes another or is going to make another request for that same resource, it's going to first check its cache and say, oh, that it was valid for 60 seconds. It's been 49 seconds now. So instead of actually making this request, I'll just grab the thing that I saved earlier. So that works. And after 60 seconds, it will go and revalidate. It will actually make that call to the server. This works pretty well, but increasingly people are kind of used to just having the latest and greatest up-to-date value of everything. So this doesn't always work perfectly well, but for a lot of use cases, this will work just fine. So another thing that we can do is stale while revalidate. So we can update the cache in the background. So this kind of piggybacks on top of the timed invalidation with cache control headers, where you could say after 60 seconds, we're going to consider it stale. But then I'm actually okay with you serving stale values for another 120 seconds. And so if the browser says, as an example, the browser goes to a CDN, and then the CDN is managing this stale while revalidate. So if the CDN sees, oh, I've got a cache of this HTTP resource, and it says that it was valid for 60 seconds, but it's now been 65 seconds since I last updated that. So what I'm going to do, because it has the stale while revalidate header, or directive on that header is I'm going to send them back the stale version, but in the background, I'm going to go to the origin server. So that way, the user who's waiting on this response, they don't have to wait for going back to the server to get the fresh version, but they're the ones who triggered refreshing things in the background. So this stale while revalidate actually is really, really effective for making sure things stay fast, even while taking into account the fact that they're going to be a little bit stale. And sometimes that's perfectly reasonable. Another thing you can do is force a fresh value. So I actually do this on my website as well. So when I'm signed in as an admin, I can add a fresh query param to any page, and it will force refresh all of the things that are cached on that page. And so that allows me to deal with situations where maybe the GitHub action didn't work, or I know that this particular the third-party cache that I have is not going to refresh for another week or something. So I can like force that to refresh if I want to. For like podcasts and stuff, I've got like a week on those, so I'm not hitting their APIs all the time. So you can force and manually update things. But one of my favorites is soft purge, and I was clued into this idea from Fastly, which is a CDN that kind of, as far as I'm aware, has popularized this idea where it's kind of like a manual stale while revalidate. So let's say that I do have stale while revalidate on some HTTP resource, like say a static web page, like my about page or something. And I have made an update to it. So I want to make the CDN update its version of that page so that users get the latest version. But I have cache headers on there that say it's valid for like 2 days, and it can be stale for an additional 3 days or something like that. So if the user comes to the page, they're going to get potentially a 5-day-old version. So what we can do is we can say, hey, I've updated this. Let's go tell Fastly or whatever CDN that this is actually stale now. Even though it's been like maybe 1 day, it's not going to actually update for another day after that. So we can just proactively say, hey, no, just mark it all as stale and immediately go and refresh it the next time somebody requests that page. So this can be really, really efficient for certain use cases. And it's just the reality of the world that we have to deal with revalidating things because our cache keys are not perfect. We can't make them perfect. So along with all this, we're talking about HTTP and web servers and stuff like that. I just want to make a little side note because I think it's relevant here. Static site generation, SSG, was really, really popular. It's becoming less popular for this reason. SSG is basically build time caching with CDN and proper cache control headers. That's all that SSG is. And it's important to recognize that it has no performance benefits over a fully server rendered site with a CDN and proper cache control headers. It is exactly the same as if you have an origin server that's generating these pages on demand and then caching it with cache headers. So if you're able to cache the entire thing at build time, then you're also able to do this from server rendering, and it's not going to have any performance impact at all. This is contrary to popular belief, so I just want to clear that up. But I actually have a note on the other side, and that is SSG also has severe limitations as your product evolves into dynamic requirements. So like it's a little box, and as soon as you go outside of that little box, you're going to have to make some major trade-offs that you won't like. So it forces you to choose between re-architecting or offering a worse UX. And so my recommendation is to just start with fully server rendered. So that's it. There you go. I'm not your mom. You do what you want. But I feel like SSR is the way to go. I do not do SSG. So there you go. A little spicy. Sorry. So let's talk about another caching problem. There's another bug. We're going to play this game again. There's a major problem in this caching implementation. So we have this get video buffer that returns a promise. Our get video buffer cached is also async, so that's not the problem. You can totally do async await and stuff like this. We're not really handling errors. That is also something you need to consider. But just the basic premise here, there's a major problem here. So go ahead and pause the video and come back when you think you got it. Okay, you good? You got it? Here's the bug right there. the video buffer cache, that object, you pretty much like very rarely want to use an in-memory object for something like this. And if you do, you want to think about the cache size because in our case, we're going to end up with some sort of JavaScript heap out of memory because we're loading video buffers into a cache and just keeping them around forever. Probably not the best idea. They definitely could be useful in some scenarios, but you just got to watch your memory. So let's talk about cache size and solutions. So one solution is least recently used algorithm, which basically whatever was used most recently gets pushed to the back of the line as far as things that are proactively ejected from the cache. And so that's the idea, is just you set a fixed cache size, and when you're going to add something into the cache, you're going to eject the thing that was used least recently. And there's a great module for this called LRU cache. This is an in-memory cache, but it manages its size so that it never gets too big. The file system is also another place to cache. It wouldn't work for our video buffer because we're literally like reading from the file system, so it's not really caching anything. But this can be really useful for a lot of different things, like compilation of JavaScript files. Babel sticks things in the node modules.cache directory. And so, yeah, using the file system for reducing amount of computation, especially when reading from the file system is faster than whatever it is that you're doing. That's a pretty common solution. And related, SQLite, also a file. Yeah, you can use SQLite as a cache, and the Epic Stack actually uses SQLite for its cache using LiteFS. And so its cache is actually distributed to all the instances of your app that are running, which is actually pretty important. And so, yeah, you can definitely use SQLite, and Epic Stack does that. My personal website does that. It's great. And then Redis is a really common solution to this as well. So it's a service that's running over here that you talk to, and normally, provided that the Redis instance is running close to where your app is, that can be very fast as well. And it is technically more than just a cache. I know the Redis folks are really trying to push. It's not just a cache, but that's what a lot of people use Redis for. Cache size can still just get exploded out of control. So yeah, keep an eye out on your cache. But these are a couple of solutions or things that can alleviate some of the pain around caching size. So let's talk about cache warming. So when you have maybe you've got a bunch of products, hundreds, thousands of products, and each one of these needs some levels of caching implemented. When you first deploy that thing and you're bringing up or adding all of the caching for all those things, that can lead to a couple of problems I want to address. So first of all, if you're talking to APIs, like maybe you're talking to the Shopify API or you're talking to a podcast API or something like that, sometimes you can get rate limited. So make sure that you are aware of the limitations of the APIs that you're interacting with, so that your IP doesn't get blocked by those providers. Because when you're bringing it all up, all of a sudden you're just loading up the cache, tons and tons and tons. So think about that. Requires a lot of resources. So like maybe if you're, it's probably a good idea to be very thoughtful about how many of those things you're updating all at once. But if not, then at least like during the warm-up process, maybe give your CPU give yourself a bit beefier CPU. But yeah, probably better just to make sure, because you're going to be warming up the cache more than you think probably. But yeah, just make sure that you aren't hogging all of the resources of your web server as you're warming up the cache. And then it also makes users wait for the fresh values. So it's probably a good idea to warm up the cache before you actually switch DNS over if you're deploying a new version of your app or something like that. So yeah, warming up the cache kind of turns this quiet, nice setting into just total chaos where everybody's doing everything all at once. So just think about that when you've got a lot of things that are cached, and find ways to slowly warm up the cache rather than doing everything all at once. So yeah, soft purge is actually a really good solution to this, where you just mark everything as stale, and then as users request those resources, they get the old version, and they kick off the refresh of that cache value. So there's also this problem where once you put something in the cache, it now could possibly be different from the thing that it's caching, because the thing that it's caching could get a change. And so this is I suppose the actual function, what it actually is doing, or the values that it's returning could technically be another key for your cache key or an input to your cache key, but that is not reasonable. So you just, what I recommend is you add some validation that will check what came out of the cache and make sure that it's what your application expects. And you can use Dodds for this and it's awesome. So just something else to think about. And then cache request deduplication. So if a bunch of people just like it's Christmas Day and now, or Black Friday, and now everybody's going to hit your product page, they're all going to be making these requests. You want to make sure that if one request is going out and that request result is going to get cached, make sure that the next person who's requesting it doesn't actually make that request themselves and they just wait for the result of the first one. This is non-obvious unless you've thought about it. So once you think about it, it's like, oh yeah, of course we'll want to do that. But yeah, this is actually pretty similar to data loader. If you are familiar with that, you can take a look at data loader as a concept. It's pretty interesting. So really what you're looking for is Cachefied. So I actually built Cachefied in kentcdodds.com as just a module. And then I invited people to like, please open source this. And so somebody did, and it's awesome. They did a much better job. And it's tested it, and all of that is good. And also added a bunch of cool things like stale while revalidate and soft purge and a bunch of other really cool things. So take a look at, and also like request duplication, deduplication, which I had not done. So a bunch of other cool things. So give Cachefied a look. It is phenomenal. Strongly recommended to check out Cachefied. Really